So, welcome back students. We are basically discussing several mechanistically important transformations, and we are saying that if you are quite familiar with the mechanism of some of the transformation, then sometimes it is very easy to formulate a retrosynthetic pathway. And basically we are discussing some unusual transformation and its mechanism, and those mechanism based transformations are very important for your exam purpose also. So, we are giving a highlight or giving a heading that transformation as well as mechanism based strategies. Now, the target molecule which I am now given is something like this, and I say the starting material will be also given to you, the starting material also given to you. The epoxide stereochemistry was not that relevant, but the problem where from I have taken it, it gives the stereochemistry. Now, if you see the target and the starting material, you will find that something is definitely can be doable, and I said that okay, we were having a benzyl group here CH2, this epoxide has to be cut down or epoxide has to be generated. So, if some nucleophile you add it here, that will basically give you this. So, what you can think about that, if you have this epoxide, you can use 1, 2, 3, 4 this CH2 minus. So, if something like this CH2 minus you can have in your lab, or maybe this compound is basically nothing, will basically equivalent to triple bond CH2X. It is basically a homopropagyl kind of bromide or alkyl anything. Now, I say we will be giving you something else. I say no, I will be not giving you this compound, this is not available in the lab. So, why don't you take this particular compound? This is basically a acetylene derivative. So, basically 1, 2, 3, 4 1 butane 1, 2, 3, 4 1 butane. Now, earlier this particular, if you are thinking of using this, you said that this compound is having a X here, X is basically a chloro or bromo, and how the way you are planning to synthesis, you are trying to convert this compound to corresponding lithium or magnesium species. So, a negative charge generates here and you will be opening this epoxide, that is fine, but you are basically overlooking in this carbon you are also having a acid yielding hydrogen, that is extremely acidic. So, when you are trying to exposing this compound with base, you might generate the lithiated salt of acetylide also, and then this might also react with this thing. So, basically you are having a regiochemical issues. Now, if I say I am giving you 1 butane, you say that 1 butane if you use, how it can give you the target molecule, fine. First think about 1 butane I have given to you, you react with a base LDA. So, basically you will be generating the minus here. Now, this minus attacks the epoxide. So, what product you will be getting? You get the OH here CH2. Now, this CH2 you will be having this alkyne. Okay. So, instead of a terminal acetylene, you get a internal acetylene as a product. Then you are in doubt, sir, your target molecule is having a terminal acetylene, you have generated a internal acetylene. Okay, do not worry, just count the number of carbon, this part is fine, this part is fine. Basically 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So, number of carbon is absolutely same. Now I am saying that can you think of some reaction so that this internal alkyne can be rearranged to a terminal alkyne. Means that I am saying that you just transfer this internal alkyne to a terminal end just by this and this. So, basically this internal alkyne has to travel 2 carbon extra from this part to this part. So, is it looking very interesting, and particularly this reaction is possible, and this reaction is particularly named as alkyne zipper reaction. Now, in zip basically, if you remember, zip is basically the zip which you use normally, you zip up, zip down. So, you are having something like this framework, you are having some bottom and this button is going through this way. So, zip is opened up and zip is closed. So, now what is this zipping? Zipping means that you are opening and closing through this particular instrument or this particular link. So, once it comes this side, the zip is open, once it comes this side, the zip is closed. So, we called zipping and unzipping. Now, the same terminology was used in a reaction named as alkyne zipper reaction. Now, for the detailed mechanism you can refer to sinarchive.com, but we will be also talking about the mechanism how this reaction takes place. So, I am saying you are having this alkyne, this we are drawing the hydrogen here which seems to be extremely acidic. So, you are having alkyne CH2 CH3. Now, I am saying I will be giving this alkyne to a strong base, the base name is kappa. What is kappa? Kappa is basically 1,3-diaminopropane, and you can use it with this potassium salt, 1,3-diaminopropane and potassium hydride you can use. Now, initially this 1,3-diaminopropane is NH minus and H plus with these things. This is basically extremely basic. It abstracts this acidic hydrogen of one of this alkyne. Now, this alkyne is having a CH2 and this methylene seems to be pretty acidic, and by this methylene, once it is acidic, what it does, it basically abstracted by this base and it gives you a alene kind of thing, and this end when it gets the electron, it abstracts this hydrogen of this 1,3-diaminopropane. So, initial step you are basically having this alene, it is basically a alene, the remaining part are similar. So, now this part is becoming your this way. Now, the same base remains here, the same base will try to do the same thing again, it will abstract this hydrogen again, it try to put the minus again on this double bond to generate the alkyne, and then this particular alene central carbon will now take this proton, sorry this here, this comes in entirely this way, yeah. So, you basically these things will be now abstracted the proton. So, now you are having this R 2 hydrogen, one is the initial step, one is the second step, you will be getting here. So, the initial triple bond is here, it is now zipped to 1 carbon right through a alene intermediate. So, triple bond now becoming 2 double bond of alene, and the left hand double bond is now becoming a single bond, and the right hand double bond now becoming a triple bond through this hydrogen abstraction. So, basically this alkyne has shifted to 1 carbon right. Now, basically what you are getting, you are now getting hydrogen, hydrogen, hydrogen. So, this methylene comes in the left and this triple bond comes in the right. So, basically this alkyne is now jipping throughout this acyclic chain. The same thing basically operates again with this same compound. You will have this NH2 or this kappa and this NH minus. So, it again abstracts the proton, the same mechanism does operate, and eventually what we will get, you basically get RCH2, this CH2 comes here and then you get this alkyne at the extreme end. So, 2 methylene. So, initial compound you are having 2 methylene at the right hand side and you have an internal alkyne. Now, these 2 methylene have shifted towards the R and the terminal alkyne, internal alkyne now moving to extreme right is basically the GPAR reaction. So, in retrosynthetic terminology, a GPAR reaction basically is something like this. If you having a CH2N here, you treat with potassium hydride and 1,3-diamino propane, and it basically unzips like this N, and at the extreme end you get this alkyne. So, a internal alkyne was transferred to a terminal alkyne. That is why we called it, the alkyne internally has been jipped to a terminal position. Now, coming to our problem which was given to you. I said initially you have given this epoxide and I say you react with this epoxide with this compound. So, initially open up of this epoxide through a base like LDA will give this minus here, this minus will attack to this and you basically will be getting this OH, CH2, CH3. So, now here the scene is ready for the jipping. So, first KH and 1,3-diamino propane. Now, see the jipping will be taking place and it is a OBN, you basically have one OH here. Now, see this CH2 will be now linked to this CH2. So, there will be CH2, CH2 and then we will be having a methyl. There will be another jip. So, I call this as a first jip, there is a second jip. So, jip will be continued till the internal alkyne is converted to the terminal alkyne. So, BNO, BNO now will give you this CH2, 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 this is having a CH2H. So, this CH2 also now coming CH2, 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 yeah. Now, the jip will be stopped. So, jip will be continued till there is a no more methylene left in the ring. So, first jip, second jip, there is a n number of jip possible and this GPAR reaction is very useful in terms of synthetic synthetic potential. So, internal alkyne like this is often converted to a terminal alkyne, terminal alkyne. And the terminal alkyne basically you can do different kind of reactions, they can be easily converted to the corresponding acetylite, you can do whatever chemistry you want. So, this jipping is absolutely very useful and that gives you a pretty nice synthetic useful reaction. So, next one we will try to give you a similar mechanism based strategies. And the problem which was now given to you, the target structure is having this. This is the target structure. When I say I will be giving you the particular starting material, I say the initial starting material which I gave it to you is having this carboxylic acid, and then I also give you a compound like methyl acrylate. Now, if you see closely, the carbon network almost remain similar. Okay, you have oxygen here. Carbon network remains similar. You have a one starting material, you have second starting material. So, it seems that somehow if this carbon you can link this particular alkylate, sorry, this methyl acrylate, you get a 2 carbon thing, 1 2, this 1 2. Now, eventually initially you need to construct this ring with this help of this carboxylic acid oxygen. So, I will now draw this retro a little bit different way, and I say if somehow it is possible for you to generate a radical here, this radical can undergo reaction with this ethyl acrylate through simple radical coupling or radical olefin coupling. Now, this chemistry we have already explained to you earlier, that how you can generate radical if X is bromo and iodo. I said if you treat this compound with Bu3SNH and AIBN, you can get a radical here. Okay. So, in particularly redundant functionality we have talked it. So, now which I am saying that now we are almost close, and I say if you have this compound you can easily generate this. Now, this is basically a, you can think about a simple FGA through radical based reaction, this is kind of a FGI, functional group interconversion. Now, so your starting material is there. Now, what you can think about? You have to introduce a iodo here, and this oxygen also should be in a 1-2 position with the iodo. Now, if you try to do a iodonium ion with this olefin, you can form a iodonium ion, then you can visualize that this carboxylic acid can act as a nucleophile, and to cleave this iodonium ion to close this ring to give you a lactone, and this iodine now comes here. So, this reaction is we also talked about is a iodo lactonization reaction. So, only thing is what we need to do, we basically need to know the mechanism of this entire transformation. So, now start with the starting material which was given to you. First iodine and sodium bicarbonate was used. So, initially iodine you basically get the iodonium ion, fine, and then as bicarbonate is there, you are having this O minus here. Now, this will instantly undergoes nucleophilic opening of this iodonium ion. So, what you will get? You get this O and this I. It could be iodolactonation, could be bromolactonation, whatever way you can do it. This is basically a lactonization reaction. Now, I am saying this iodo compound can be easily cleaved through Bu3SNH AIBN. This heterolytic bond cleavage is possible, and what we are getting? You will basically get a radical here, is not it? Now, this radical can easily be reacted as another starting material is giving you a ethyl acrylate. This radical usually reacts through to this double bond, and you get a CH2, CO2 Me, you get a initial dot here, this radical. Now, this radical is definitely stabilized by the caprodative effect of this CO2 Me group. Now, you are having solvent or Bu3SNH, which can abstract the hydrogen, and then you basically get the final product. The final product structure was given to you CH2, CO2 Me. So, that basically closes your synthesis. So, in this particular synthesis, what are the things we have seen? We have seen that a radical based carbon carbon bond forming reaction is very important. We have used it, okay. And then also we use our earlier reaction, the transformation iodo lactonization, which you have used it. Now, similar kind of thing, now I will be trying to explore a very simple problem. I say you have to make this compound starting from this compound without using Me2Cu-Li or without using the Gilman's condition. Now, then you are thinking that okay, this is a bit difficult, how you can do it, because 1,4 Gilman is the normal way you can use it. I said okay, do not get confused. The target was given as this one, starting material was given this one. So, you need to think about something. So, I say, is it possible? You said that okay sir, you are making a cyclopropane kind of thing, and then how you can keep this cyclopropane. So, now cyclopropane are basically, as I said, they are strained ring. There is absolutely strained ring. Cyclopropane ring is absolutely strained, and they often behave like a normal olefin. They are more of a pi character than the usual sp3 hydrocarbon. So, I say if you can open this thing here, then it is absolutely possible. So, first your starting material was given here, you do a simple Simon-Smith reaction, which is known to you, CH2I2 zinc copper couple, right. So, basically what you get here we will explain in the next slide. So, first you get this compound, do a Simon-Smith reaction, or even you can do a carbene addition. So, Simon-Smith you will basically get now the cyclopropanes are absolutely strained molecule, and they often behave like a more of pi more of pi olefinic unsaturation. In principle, you can basically clip this compound with hydrogen palladium charcoal. Now, palladium charcoal, what it will give? It can clip here as well as it can clip here. So, you basically can get this compound as well as your ring might be extended. I mean, if you clip this way also, that also you can get the corresponding 7 member thing. You can get the 7 member things also. So, now as I said, our desired molecule is this. Actually, there is a other way to clip this. Now, all of you know that sodium liquid ammonia is basically the Barch condition, the Barch condition. Now, Barch condition you will basically getting a single electron. Now, this single electron will try to clip this cyclopropane through a radical pathway. Now, if you see how these things will be, it basically clips this particular bond and will give a dot here, give a dot here. Okay. Now, I say the dot on this carbon is basically stabilized through this caprotative effect of particularly this carbonyl compound. So, it is the radical was somehow kind of stabilized, This is the main thing. That is what. Now, you can also have this radical cleavage here to get the cycloheptane also. Now, I see if you have this radical which can clip from particularly this thing, you get a CH2 dot here. Now, sodium liquid ammonia will give you another electron to basically will give you this minus, or even in this particular point you can now have a tertiary butanol which will now act as a proton acceptor and you get this methyl. Now, this thing this particular radical which is now generated here, this also can initially be a hydrogen, and now this is absolutely stable. If you have a this carbon ion, this also can be easily will give you the corresponding enolate which you now pretty well known. This stepwise, now this particular radical can again accept this another electron to give you the hydrogen. So, in this way you are having a electron. So, this way basically you can clip this particular cyclopropane, and cyclopropanes are always strain intermediate, they can be easily clipped. The only thing is the Barch reduction mechanism you should be quite familiar of, and it can be you can basically make both the molecules, either this one as well as this one depending on the reaction condition, and if you have to make this one, probably you can try using this without the Gilman. Gilman definitely you can do, but as I said, if you try to avoid the Gilman, you follow this pathway and this will give you a nice access of this particular dimethyl thing. So, we will try to continue our discussion on the mechanism based strategies, and we will come back in the next lecture. Till then, goodbye.